In this video, I will explain the reaction rate and Maxwell-Boltzmann distribution curve and how the different factors that affect the rate of the reaction will affect the shape of the curve. This is for A-level chemistry. So let's first recap what we've learned before from GCSE chemistry about reaction rate. Reaction rate is the change in concentration or the amount of reactants or product over time. The rate of the reaction can be measured using the amount of the reactant used or the amount of product produced over time. So the rate of the reaction can be the amount of reactant used over time, or it can be measured as the amount of product formed over time. The quantity of the reactants or products can be measured by the mass in gram or by the volume in centimeter cubed. So it will be gram per second or centimeter cube per second. You can also use the quantity of the reactants or products in terms of the moles. To find the rate of the reaction graphically, you can measure the rate of the reaction from the graph if you draw the tangent at a certain point in the reaction curve, and then you calculate the slope of that tangent. So the slope will be the change in y over the change in x, where you have the time on the x-axis and the amount of product in this case on the y-axis. And this is the tangent at this specific point in time. So this tangent here, we calculate the slope for this one at the change in y over the change in x. According to the collision theory, the chemical reaction can occur only when the reacting particles collide with each other with sufficient energy. So they have to do for collision, and the collision have to have sufficient energy. So the rate of a chemical reaction will depend on the collision frequency of the reacting particles. So if there are more collisions, then the reaction will be faster, and also the energy transferred during the collision. Remember that the minimum amount of kinetic energy the particles need to start the reaction is called the activation energy, which is enough to break the bonds in the reactants to start the reaction. So when we look at the energy profile for any reaction, the activation energy here, which is the difference between the energy of the reactant and the top point in the curve, this is the minimum kinetic energy required for a particle to start the reaction. Reactions which have lower activation energy will have higher rate than reactions which is going to have a higher activation energy. This is because more particles will have kinetic energy higher than the activation energy. So what's Maxwell-Boltzmann distribution curve? This is a plot of the number of molecules in a gas versus their kinetic energy. So on the y-axis we have the number of molecules, and in the x-axis, we have the different kinetic energies of all the particles. The area under the curve is equal to the total number of molecules. And the top point here, or the peak of the curve, will represent the most likely energy of a single molecule. So this is the energy the highest fraction of molecules will have. This curve will always start at the origin 0, 0, because there is no particles that are going to have zero kinetic energy, meaning that it always will has to start at the origin. And then we have the activation energy here for any reaction, for a specific reaction we're talking about. So this is going to represent the activation energy, and then the area under the curve to the right of the activation energy represents the number of molecules or number of particles that are going to have kinetic energy higher than the activation energy, meaning these molecules or this part of the molecules to the right of the curve are the ones that are able to start the reaction or are able to react. However, this white part here represent most molecules which are going to have energy less than the activation energy. So only the part to the right of the activation energy represents the molecules that are going to react. So what are the different factors that affect the rate of the reaction? The main factors are the concentration in case of solutions and pressure in case of gases. And then we have the temperature and then the use of a catalyst. So first of all, temperature, we know that when we increase the temperature, the rate of the reaction will increase. This is because when you increase the temperature, the particles on average will have higher kinetic energy. So they will start to move faster. And if they move faster, then there will be more frequent collisions between the particles as well. So they have two reasons for why the higher temperature increases the rate of the reaction. This is because higher kinetic energy, which means more particles will have kinetic energy higher than the activation energy, and also because of the more frequent collision. So even a slight increase in the temperature will lead to a big change in the reaction rate. So how does the increasing temperature affect the shape of the Maxwell-Boltzmann distribution curve? When we look here at the green curve, the green curve represents the curve for the particles when we have increased the temperature. As we can see that the curve is more skewed to the right by the increasing in the temperature. And now more particles will have kinetic energy higher than the activation energy. Although the total number of particles in general haven't changed, but the number of particles that going to have kinetic energy higher than the activation energy will increase, and we can see that the area under the curve to the right has increased. The second factor is the increasing the concentration in case of solution or pressure in case of gases. Both of these will increase the rate of the reaction. In case of solution, if the solution is more concentrated, that means particles will become closer together. So more particles will knock about in the same volume of the solvent. So there will be more frequent collisions. In case of gases, when we increase the pressure, the same number of particles will occupy a smaller space. So particles will become closer together and there will be more frequent collision also. So in both of these cases, because of the more frequent collisions, the rate of the reaction will increase. So how does the increase in concentration affect the shape of the Maxwell-Boltzmann distribution curve? As we can see here, the activation energy doesn't change. However, the number of particles will change in case of increasing the concentration, which means the curve will be higher up here, and then you're going to see that the number of particles that have kinetic energy higher than the activation energy will also increase, which means the rate of the reaction will increase. What about the use of the catalyst? Using a catalyst will increase the rate of any reaction. A catalyst is a substance that will speed up the reaction without being used itself in the overall reaction. So it's not part of the reaction equation. A catalyst will increase the rate of any reaction by providing an alternative pathway for the reaction with lower activation energy. So now more particles will have kinetic energy higher than the activation energy. So how does the use of a catalyst affect the Maxwell-Boltzmann distribution curve? You can see that when we use a catalyst, the activation energy will be shifted to the left here. So this is the activation energy, lower activation energy due to the use of the catalyst, and this is the original one without the use of the catalyst. The area under the curve now, after the use of the catalyst to the right, you can see that there will be more particle, bigger area under the curve, so there will be more particles which are going to have kinetic energy higher than the activation energy, so the reaction rate will increase. The shape of the curve itself will not change at all because the kinetic energy of all of the particles will not change. It's just the activation energy that will be shifted to the left or will become smaller. So how can we measure the reaction rate experimentally? So the first way is by timing how long a precipitate takes to form. This is when one of the products is a precipitate. We can see here you can watch a mark through a solution and time how long it takes for this mark to be completely obscured. When we react sodium thiosulfate with dilute acid, one of the product is sulfur, and sulfur is a precipitate, yellow precipitate. So you can time how long it will take for this the cross drawn on a paper under the reaction vessel. How long will it take until it's completely obscured? This is, of course, very subjective because different people will have different opinion at when exactly the mark has been completely obscured. The second method is by measuring a decrease in mass. This is when one or more of the product is a gas. You can measure the rate of formation of the product using a mass balance. So you have the reaction and then one of the product is a gas. The gas will be given off and the mass or the overall mass of the reaction will decrease. This means that you can measure the change in the mass or the mass of one of the products and you can time that. So this is you will be able to measure the rate of the reaction. This is, as you can see, will be more accurate and it will be easy to do as well. The third method is by measuring the mass of the gas given, the volume of the gas given off. So one of the products here is going to be a gas and you can use a gas syringe to measure the volume, not the mass in this case, the volume of the gas being produced. So one of the product is a gas and you can use this gas syringe to measure the volume of the gas produced. Again, this is going to be accurate and also easy to do.